Okay, so when you go to Cy Davis and you look under beta again, hold on a second. You go under beta and files. For the Mac, you want to take the DMG file, but for the PC, you want the MSI file. Okay, so the second one here is for the PC. The first one's for the Mac. If you want the source code, if you're a computer science major, you know how to do all this. Just download the source code. Okay, but if you have Linux, if you know how to install in Linux, you probably want the source code. Okay, and you download it, and let me run it. That's not on my. Hold on a second. Let me run it on my computer, so you get to see what it looks like. Okay. I just got to find it. Sorry, I thought I had it. I thought I had it. Just give me a second. It's opening up. It's a little more confusing using it on the Mac than the PC. But it's free and it can do anything. It's much more powerful than graphical analysis. Okay. So here's Cy Davis. Let me make this window bigger. So, for example, let's say I want to enter data. And let's do the y-axis. Okay, so if I want to create a graph, click on the y column, and I go plot, scatter, and I have my graph. You see how quick that was? So there's my graph. Of course, I gotta label all this stuff, right? I gotta say, I don't know, time, seconds, apply, okay, and then this axis, I'll just make distance. And you put a title, distance versus time. Notice I'm always writing the units in. But this is how you want to label everything in your graph has to be labeled. You don't have to have the left-hand side with numbers on it anyway, but that's how this one is. So you can change the graph a lot. So for example, if I want to change the data points, I can change it to diamonds. I can change the fill color to red. I can change the edge color to red. And I can change the size of the points. Okay, so there's my graph. So now I need to do a curve fit to make this bigger. Now to make a curve fit, it's a little bit more complicated. So I go under tool, I go under analysis, sorry. And it depends on what kind of fit you want to do. If you want to do a linear fit, it's very easy. You just go fit linear, and it does the fit for you. But you need to put in, you need on the graph, you need to show the professor, the person reading the lab, what your fitting parameters are. So on the graph, oops, wrong window. On the graph, you want to actually type in what your fitting parameters are. Let me screw up one of the data points. I want to do it again. Let me do the curve fit again. I'm going to delete this fit, sorry. I want to mess up my data a little bit. Okay, let me do the curve fit one more time with messed up data. So I'm going to go tools, analysis, quick fit, linear. Okay, so now if you can, I don't know if you can see that as a small window, it shows me the curve fit results. And I'm going to type the curve fit results into a window here. I'm going to add text on the active layer. And when I look at the curve fit results, it says that the slope is 0.9714. And this thing has symbols somewhere. Plus or minus 0.0457. All right, slope, y-intercept is 1.228. Plus or minus 0.2306. Make the font size big so it's easy to see. Okay, so you guys can see the slope and y-intercept. All right, y'all see that? So I made my graph. How long did it take me? 10 minutes? Maybe less? So these are the graphs. You're going to have to create the graph with this software if you're using Davis. Now, remember from Physics 205, what I've done here is incorrect. How should I quote my slope? How should I quote my slope here? This is what I've done is incorrect, right? Because I have the slope and the uncertainty. To how many decimal places should I quote my slope?
3.
Is it 3 or 2?
Or, oh yeah, okay, it is 2.
Right, because the uncertainty is to the 100th place. And then this is a 5, so I actually got to round to the nearest even. That's our convention. So I really got to write down my value like that. And I got to put units in. Right? I need to write units in. I didn't write the units in. Now, what about my y-intercept? How many decimal places is my y-intercept? Is there 1? So that's the correct way to write down the curve fitting parameters based on what my curve fit results are. Okay, so this is what you'll be, and so then you take this graph, you go to edit, copy, and then you would paste it. Hold on a second, my lab report moved. My computer's acting strange. So I'm going to copy my graph. Let's say I'll put the graph here. I'll paste it there, and there's my graph. Now, and that's what I want to see in the report. I want to see this graph there. And you can get rid of the border if you don't like the border, whatever. But one more thing I ask for my students regarding the graph is a figure caption. Every graph has to have a figure caption. Okay? Every graph needs a figure caption. The figure caption has got to tell me what you graphed, what were the results of your curve fit, and if applicable, do the results of your curve fit, does the data agree with the theoretical curve fit? Okay? Because otherwise, students just put a graph students put a graph and don't say anything about it. Even if they have to write a conclusion, they say nothing about it. Even though the graph summarizes all your data, tells you everything you want to know about your data, and it's the graph that allows you to make conclusions. And then in the past, students would just put the graph there because they were told to, now realizing that thing is important. And so I want you to write a figure caption. Every graph has to have a figure caption. Now, some graphs are just for show, but some of them provide a lot of information. And so you want to say, what kind of information can you extract from it? And if there's a curve fit that's related to a theory there, you want to say something about, does your data agree with the curve fit you chose? Make sense? And all this is spelled out in your syllabus too for the lab. Okay, so I showed you the graph. So you're expected to make graphs, copy and paste the graphs into your lab report. And then I try to make the lab reports formal so that, what happens when you guys transfer, you guys tend to be ahead of the game. You guys do much better than the other transfer students. That's according to students that have come back and talked to us. Okay, so let me talk about the experiment. We are going to be looking at Ohm's law. We're going to learn how to protoboard is wired. So let me show you what the protoboard looks like. Let me change views again here. So my protoboard is different. So some of the things, so when I was designing this lab over the summer, Tyler gave me some equipment, but the equipment that I have is a little bit different than what we ended up buying. So the protoboard is basically a board with holes on it that looks like this. So you're going to build your circuits on this board. All the circuit wiring labs, you're going to wire them on a board that looks like this. Yours is more square than mine. I think yours is about half as long as mine, but a little bit wider. So you should have one of these. But before you can use this, you actually have to know how it's wired. So there's a bunch of holes in this board, but on the inside, the holes are connected together. Certain holes are connected together, and certain holes are not connected together. So you need to figure out how the holes are connected together. So the question is, how do I figure that out? How do I go through the process of figuring out how the holes are connected? This is where you use the multimeter. If you use a multimeter, and I'm missing a wire, hold on a second. Somehow my wires disappeared. Oh, here. So if you're using a multimeter and you measure resistance, if I were to measure the resistance of this wire, what do you think the multimeter would tell me? What do you guys think? If I measure the resistance of a wire with the multimeter, what would it tell me? What do you think the resistance will be? So I'm doing this right now. Any guesses? A small number, correct. You put on the lowest scale, and mine reads 0. In fact, if you use the other one, if you use the big multimeter, there's actually a setting for measuring continuity. There's actually a setting for measuring continuity. Okay, I have it on that setting. So it'll beep at me if I have continuity. You hear it? In fact, mine's reading 0.0005. Let me turn that off. It's annoying after a while. And if I break the continuity, what's it going to read? It's going to read OL. Or you'll see, if you don't have continuity, you're gonna get something like that. Okay? So what you're going to do, you're going to take the multimeter and you're going to look between pairs of holes. Okay, you don't have to do every single combination. You will see a pattern. And you're going to measure where the resistance is essentially 0. Okay? And when you see that, then you'll know how the holes are connected underneath. Right? The holes are connected underneath the board a certain way. So what you have to do is go through and use the ohm meter to measure whether you have 0 volts. If you have 0 volts, the holes are connected together. So that's the first exercise you have to do. So for the that's the Protoboard part that you see in the lower left-hand corner of the screen. So you have to show me how they're connected. You're going to go through and do through the exercise and show how the Protoboard is connected. Now, this Protoboard picture that you see here is different from the one you got. The one that you see in the figure is actually a better one because it has an extra area where you can connect the power supply. So this stuff up here, ignore. This is where you actually connect the power supply. But you don't have that feature here. Okay? You don't have that feature here. So ignore that part. All you got to do is see how this board is connected. This board is the same as the board we bought for you in terms of how it's wired. Okay? So I want you to go through and ohm that out. That goes real quick. And then you just, using drawing lines, right, in Word, you can draw a line to say how they're wired. Does that make sense? Yeah, so the resistance will be a small number if they're connected together. It won't be exactly 0 because 1, the connection is not perfect, and 2, the wire has a finite resistance. And there's a finite resistance inside. Okay? Once you know how that's wired, then you can build a circuit. And so in part 2, what you're going to do is use Ohm's law. So you have a 1,000 ohm resistor, which is one of these guys. See how tiny that is? How do you know it's a 1,000 ohm resistor? Well, obviously you have to go through and measure it. But you have a bunch of resistors in your kit. You have to go measure every single one. Actually, the resistors are color coded. There's a color coding for the resistors. The newer ones, the color coding is different. And there's a card that came with your lab packet which tells you what the color coding is. So make sure you use the card because you're going to have to use that color coding several times a semester. So a resistor, which is a device that limits current, that obeys Ohm's law as long as you don't put too much current through it, you'll see a color code. For example, let's do this. You'll see red, black, red like that. Okay? And I forgot to take out my color code. Let me see if I can grab it real quick. Anyway, these all stand for a number. This is the first digit, this is the second digit, and this is an exponent. But let me tell you what the color code is before I go on. And I don't have it memorized, so I know the first few. So the color code is black, brown, red, orange, yellow, green, blue, violet. I always forget the last ones. It's either gray or white or gray. There's a 0, 1, 2, 3, 4, 5, 6, 7, and then there's 8, 9. It's white and gray. I forget them. Okay? So the red tells you the first digit. First digit is 2. This tells the black is the second digit, 0. And then this one tells you the exponent, 20 times 10 to the second, which is 2,000 ohms. So in your lab kit, you should have a resistor. You should have a resistor that's brown, black, red. That one's a 1,000 ohm resistor. Okay, if it's brown, black, red, it's a 1,000 ohm resistor. You don't have to measure them every single one out. Okay, that's why the color code helps you a lot. Okay, because if you had a whole pile of resistors, you didn't know what the color code is, you'd be in trouble. Okay, so you use this color code, and again, you have a card that tells you the color code. Now, there's a fourth band on most of them, on all of them, and the fourth band tells you how well that number is known. Well, I think gold is 1% and silver is 5%. So if you have a gold band, then that means that this value is known to within 1% of the value. So if the last one was gold, it would be 2,000 ohms plus or minus 1%. Okay? So you all have to learn how to use the color code on the card. The card is provided in the lab kit. So what are you going to do in this lab? You're going to actually take your power supply and you're going to say, well, where the heck is the power supply? We have a funky power supply. Again, we're trying to go the cheap route, right? We're trying not to make the lab kits expensive. Your power supply is like an adapter. Okay, your power supply is this adapter. And in fact, if you look at it, you see a switch on it. You see that, if you can see that red thing. Okay, that red switch, it's not a switch, but that red dial, which you have to adjust with a screwdriver, will allow you to vary the voltage. There's only 6 settings on this. So you can only get you can only get 6 data points in your lab. Okay, for this lab, you can only get 6 data points. And so what you're going to do is you're going to wire a circuit on this protoboard. So you're going to put your resistor in your board. And you're going to figure out how to use the multimeter and the voltmeter to wire this up and measure voltage as a function of current. So, let me erase this stuff. So yeah, I'm going to draw it as a battery. Here's your power supply. And so your power supply goes in increments of 3 volts, 4.5 volts, 5 volts, 6 volts, 7.5 volts, 9 volts, and 12 volts. Those are the only voltages you can use. You're kind of stuck. Okay. Now, I ought to warn you because I screwed it. I messed up yesterday because I was playing with this. So the connectors on the end connectors are especially made so you can actually stick them in the protoboard. They're very delicate and they break easily. And I don't know if you can tell, I broke one off last night. Okay, I broke one of these last night. So be careful with it. Because if you break it, you're not going to be able to use I guess you can put it in your protoboard. You can actually cut this wire off. You can just cut the end off and use strip the cable. And you can still use it, but it's going to be a little bit more challenging. So you're going to wire your circuit. You're going to have the wire from the power supply. It's got to go to your resistor, right? The other end of the resistor goes to the ammeter, one end of the ammeter, and then the other end of the ammeter goes back to the other side of the power supply. So now you have a closed path. So you want to use the good ammeter here, the better one. Of course, you got to do it right or you blow a fuse. And then use a cheapy one to measure voltage. And so what you're going to do is create a data table. It's not a big data table of voltage as a function of current. And if the resistor obeys Ohm's law, you should have got a straight line. And guess what the slope is going to be? What's the slope going to be if I plot that? What's the slope going to give me when you do the curve fit? Resistance, yeah, so the slope is the resistance. Okay? So, but the graph, the curve fit is not only going to give you the slope, the resistance, but it's also going to give you how well it knows it. It's going to give you the uncertainty. So, if my color code says 1,000 ohms, but my slope says do those two values agree? If the color code is 1,000 ohms, and this is 998 plus or minus 1 based on my experiment, do these two values agree? Yeah, why not? Why don't they agree?
You get a range of 997 to 999 with that uncertainty, which does not fall, which 1,000 does not fall into.
You're correct. Okay, right. So anytime you make a measurement, you're not really getting a single value. Anytime you make a measurement, you're actually measuring a range of values. If your range of values does not include this value, then it doesn't agree. However, one of the things though I forgot to tell you about is, or I did tell you about is, there's a fourth band here, right? Let's say the band is gold. Gold means 1%. What's 1% of 1,000?
10.
10. So really, do they agree now?
So the ranges just have to overlap somewhere.
Yeah, they overlap. So they agree. Because I didn't tell you about, so I kind of was, I was misleading, right? On purpose though. I got to take into account that, right? I got to take into account the fact that that resistor has a fourth band that tells me how well it's known, right? Now, of course, if I did this, if I had this, they don't agree. Okay. I want to say some things about this when you're doing this measurement, okay? Just like when you're using a thermometer, right? When you're using a thermometer to measure temperature, let's say you have a container full of water, a big container full of water, and you put a thermometer inside. You want to measure the temperature of the water. You do not want the thermometer to affect the temperature of the water. Isn't that true? Because otherwise it's going to screw up your measurements. Well, the same thing here. I do not want my voltmeter to affect my voltage measurement. So the voltmeter has to have special properties so that the measurement is not affected. So what is that special property? Well, first of all, you don't want the voltmeter to draw any current in this direction. Because if the electrons are going this way and you're giving it, and it reaches this point, this is a branching point, if some of the electrons go this way, then you're taking away the current from this guy. That's going to make your voltage smaller than what it should be. So ideally you want the resistance of the voltmeter to be infinite. It's not, but it's huge. So the resistance of the voltmeter is giant. It's like 10 to the 8th, 10 to the 9th ohms, depending on the voltmeter, depending how good it is. The better the voltmeter is, the higher this is. So you don't want the electrons to get to this point and take the path this way. You want the electrons to continue along the same path through the resistor. So it's that you want this as if it doesn't do anything to the current. You want the electrons to behave like this guy's not there, so I'm just going to go this way. So the voltmeter itself has a very high resistance. And if this is 1,000 ohms and this is 10 to the 8th ohms, you're not going to notice it at all until maybe the 4th or 5th decimal place. Okay. So the voltmeter has to have a very high resistance. Okay, the old voltmeters are not like that. Okay, so there's a problem in some cases. Now the ammeter also should not affect your circuit. Whatever goes through a resistor has to go through the ammeter in order for you to measure the current. It's got to be in series. But this thing cannot impede charge flow. Because if it does, then you're not getting a true reading of what this thing is doing. So this has to have a low resistance. There's 3 settings on your meter to measure current. All the settings can measure the current in this circuit. Well, not the 10 amp one. I stand corrected. Okay, not on this one. This one's not as good. On the 10 amp one, actually has the lowest resistance. The meter has actually the lowest resistance. Because you have a very large current means low resistance anyway. So this has to have a very low resistance on 10 amps. So you have a 20 milliamp scale, a 200 milliamp scale, and a 10 amp scale. Okay, on the 20 milliamp, so when you do the measurement, you're able to get results on the 20 milliamp scale and then the 200 milliamp scale. And what you should do, because there's only 6 data points, okay? You should see how the results differ between the 2 scales. You will find that if you do this measurement on the 20 milliamp scale as compared to the 200 milliamp scale, you will have a higher resistance, slightly higher resistance on the 20 milliamp scale because the resistance on the 20 milliamp scale is higher. The resistance on a 200 milliamp scale is lower, but the 200 milliamp scale gives you less sig figs. There's a trade-off. Okay, there's a trade-off, so you got to think about that too, okay? So even though you go to 200 milliamp scale, you get lower resistance, you get less sig figs. The question is, is it worth it? Okay. So that's something for you to think about. Because when you're making a measurement, you got to think between your precision and accuracy. Which one's better for you? Yeah, you're going to measure the voltage and resistance at the same time. I'm sorry, yeah, you're right, the voltage and the current. You're going to measure the voltage and the current at the same time, okay? It makes it easier for you. It is going to be kind of a pain to work with this because this is not a simple power supply. You actually, every time you have to actually unplug this, take a screwdriver and change the voltage and then plug it back in again. So it's kind of annoying, but you only have 6 data points. Does that make sense? I'm trying to give you all kind of details as I can regarding what you should observe. Okay, and you can go through this video over and over again if you remember the details. These are important details, especially when you're making sensitive measurements. And a lot of times they're not discussed in the book or in a manual. Okay, so that's part 2. Part 3, yes, there's 4 parts. And part 3, same process, except that you're replacing this guy with a bulb that we provided for you. This time the graph won't be linear because it doesn't obey Ohm's law. It'll look like this. Although it's going to be hard to see that. And the reason why is because you only have 6 data points. And we gave you a landscape, the bulb we gave you is a landscaping light because it can run at 12 volts. Okay, you can't do this experiment with a 120 volt bulb and put 12 volts across. Okay, so I had to get you a landscaping bulb. Now, what I want you to do is try different fits. Okay, so try different fits for part 3. Try different fits. But, and students do this all the time. You should have no more than 3 fitting parameters. You know, you should have no more than 3 fitting parameters. You know, you can fit to y. Don't fit to y equals mx plus b, but you can try this. I mean, you could try something like, or just b plus b if you want. And see what works best. Students will give me a 12th degree polynomial sometimes in this lab. It's useless because how the heck are you going to interpret all the parameters? How are you going to interpret what the computer, you tell the computer fit to these, the computer spits out these numbers and the uncertainties. What do they mean if you have 12 parameters? I can fit anything to a 94th degree polynomial, but what the heck do what the heck do the curve fitting parameters mean when you have 95 curve fitting parameters? Okay, so I'm just for this part, I'm trying to just get you to analyze and interpret. The interpretation does not have to be correct. I'm just trying to get you to analyze, and then you tell me which curve fit works best. Okay.
Professor, do you want us to show us, or not show, paste the graphs of every single one of those and explain why the best one is the best?
You don't have to. You can just tell me which one works the best.
Okay.
And then I'll, you know, because different students might have different results depending on how well they collected the data. Okay, the results might be different based on how good a job they did in collecting the data. You might have to use electrical tape to connect the wires to the bulb, because the connectors on the bulb, I think mine's different than what you got. When I was doing this over summer, I was trying to figure out what I can do, what I can use to do the experiment. I tried it with those little light bulbs. And I put 12 volts on one of those little light bulbs, and guess what happened to the light bulb? 12 volts on a 3, yeah, it blew up. So I can't do that. So this will work. Okay, these work nicely. They're going to draw more current. So be careful. These are going to draw more current than in the first part. Don't drop them either, because if you drop it, it'll break. So that's part 2. Okay, so you're looking at a material that doesn't obey Ohm's law. So you're learning how to look in this lab. You're learning how to wire circuits.
Hey, Professor.
So, not enough. We're not doing a lot of analysis. Go ahead. I'm sorry.
On my, actually, one of the light bulbs is like just burnt out from when I got it.
Oh, one of the little bulbs?
Yeah, one of the little ones.
Yeah, I have the same thing.
So, I mean, what should we do for I guess for the multimeter lab and for lab 2 or 3?
Well, how do you know? Did you connect the battery to a single battery to the bulb and see if it doesn't go on?
Yeah, and it didn't go on.
Okay, because when you do the 2 bulbs in series, you won't see them go on in some cases because the resistance is too high.
Yeah.
But if you hook up a battery to one and it doesn't go on, then what you can do is email Tyler, okay, and see if you can make an arrangement to get another one.
All right.
Okay. Just email Tyler and tell him, look, just T. Hickox. He's actually I actually a person. He's actually part of the class. So maybe let me type his email address. He's our instructional assistant. He makes all the videos and stuff. Well, most of you guys know who he is, but let me give you his email. He's usually around on campus. If you email him, he will maybe try to make arrangements for you to get another bulb. Okay? Or he'll tell you you can get it at this place. Depends on what we have left. We have some left. Okay. Yeah, one thing is be careful with the equipment. We do have some extras, but not a lot of extras. So to contact him, he can get you something, okay? He might have you, he might just have you show up at the door and he'll just stick his hand out the door and give it to you. All right. Okay. So again, for the second one is only 6 data points. If you're using graphical analysis does all these curve fits, and so does Cy Davis. Let me go back to Cy Davis. If I go to Cy Davis and they go to analysis, oops. And I go to quick fit, it can do an exponential growth, exponential decay, or a polynomial fit. But you can also define a fit. I mean, the number of fits you can do in this program is unbelievable. You can do, you can create your own function and type it in here. There's a bunch of built-in functions. There's some basic ones. Some of them are not so basic, but they call basic. I don't know what the plugins are. So it already has a lot of built-in curve fits, but you might have to type some in. There's somewhere you're going to type in your own fit, so that's fine. Okay, so this thing is really powerful. All right, let me go back to the lab. And I'm going to ask Tyler to make another video for this lab, just in case, because the way I'm doing things here is a little bit awkward. The hardest part of the lab is going to be wiring the last one. This is going to be harder to wire. So we're going to be using a diode, another material that does not obey Ohm's law. And what is a diode? Well, a diode, actually, if you look at it, and again, I forget which one they put in your kit, is a device that lets current go in one direction only. It kind of looks like this, and it has a band. If the diode's black, if this is black, the band will be gray, and the band over here means the current's going to want to go this way. Okay. So this is a diode, so it only lets current go in one direction, and when the current is flowing through it, the charge is flowing through it, the voltage drop, the maximum voltage drop, is between 0.2 and 0.8 amps, depending on the type of diode that we've supplied to you. So you're going to build a circuit, you're going to have 12 volts, and this has a 12 volt setting on it. So you're going to take 12 volts and run it through a resistor, a 560 ohm resistor. So so it's going to be green, blue, brown. Okay, it'll be green, blue, brown. Okay, so then this is the hard part. You're going to go through a special resistor. This special resistor has 3 pieces to it. So again, Tyler got you a different resistor. Yours actually is easier to work with. It has 3 terminals on it. Let me redraw that. Okay, there's the ends that give you the full resistance, and then there's one in the middle called a slider that you can move back and forth. This is called a potentiometer. So if you connect one part of the positive of the battery here and the negative of the battery here, then you get the full resistance. And this is a one kilo ohm pot. I think yours is a dial one. Mine's a really teeny screwdriver one. Okay, so you have 1 kilo ohm, and this thing will allow you to split the 1K up between 2 different values. So if you're closer to this end, you'll have a lower resistance, and here you have a higher resistance. If you move this slider to this end, then you have a lower resistance here and a higher resistance here. So you got to use all 3 terminals. So this is going to be the hard part for you. So there's 3 terminals on it. You're going to take the middle one, right? The middle one is going to go to an ammeter, and then it's going to go to the diode, and then it's going to go to ground. And then you're going to measure the voltage like that. So current's going to go, some of it's going to go this way, some of it's going to go that way, depending on what this is set to. Okay? And what you're doing is just limiting the amount of current going through here. So this will not turn on until the voltage drop across it is a certain value. If you plot I here and V here, the graph looks like this. You're not going to do this part. By the way, you see table 4? Do not do the stuff for table 4. Okay? Why? Because your multimeter, the one that we purchased, because we couldn't get the one I wanted originally, does not have a microamp scale. So in part 4, do not do table 4. Ignore part 4, step 3, because the multimeter, you don't have a multimeter with a microamp scale. Okay, when I did this over the summer, I had a multimeter with a microamp scale, and we found out that we couldn't get it in time. That multimeter was awesome. Okay, but we got stuck. We got a cheaper one. Okay, I mean, this is still pretty good, but it's not as good as the one I had originally. So you want to ignore that part. So what you're going to be in a 20 milliamp scale. You have to be on this scale. Okay, this has to be on a 20 milliamp scale. And then what you need to do is you're going to vary the potentiometer and you're going to measure the voltage here and the current here. And let me tell you, this is an exponential growth. Which means that this thing, once it turns on, the voltage changes, the current changes rapidly. So once you get to about 0.1 volts, you got to take teeny tiny steps. And so you got to turn this thing really barely, and you'll see a small jump here and a huge jump here. If you want to be able to do a curve fit to this graph, you actually have to pin down the sharpest area of the graph. Okay? And in fact, if you were to do a curve fit, and I think I better stop here, I'll talk about it next week some more. If you do a curve fit, your curve fit looks like this. This is where you have to define your own curve fit. I'll talk about this next week because I'm out of time. It's an exponential, that's an N, sorry. So when you do this, this will be a fitting parameter. You'll have a fitting parameter up here too. Okay. I'll talk about this graph next week, but you have to take a lot of data points over here to be able to pin down the graph. Because if you don't take a lot of data points here, your curve fit is going to be really bad. Anytime you do an experiment and you want to fit something to a theory, yeah, you want to use the good meter for measuring current. Okay. Anytime you want to fit to a theory, you want most of your data points in the sharpest point of the graph.
Which one's the good meter again?
The big one.
The bigger one?
The bigger one. So, this is good compared to the other one, okay? Right? So this is good compared to the other one. Because the other one only has a 10 amp scale, so you won't be able to read anything. This one has 3 scales, but I don't warn you, and the 10 amp scale on here has no fuse in it. Okay? The 10 amp scale on here has no fuse in it. So don't hook it up to something that's running, that has more 10 amps because you'll smoke this thing. Okay? I don't know why, that's a bad feature. I guess that's why they're not as expensive. So to me, the hardest part will be wiring this thing. Because you have to learn how to use a potentiometer and learn how to use a diode. And again, in this lab, really the focus is more on you're learning the skill of wiring as opposed to the analysis. The next lab we do, you'll be doing analysis and wiring. Normally, when we do this on ground, this is a 1-week lab. Okay, normally I do this in a 1-week lab, but then I don't do part 1. Part 1 is in the next lab usually. But because of the way we have the structure of the lab, I moved the part 1 part from the other lab to this one. Okay. Do you guys have questions or concerns? Okay, so remember, you're going to have 3 graphs with curve fits. You want to extract your results to the correct number of correct number of decimal places, because the software not only gives you the curve fitting parameter, but it gives you the uncertainty in the curve fitting parameter, which tells you the error in your results. Okay, this
actually I have 2 questions.
Yeah.
So the first question is for this lab 3, do we use the 3-volt bulbs again?
You won't use the bulbs.
Okay, so we don't use the 3-volt bulbs again.
Yeah, actually, let me think. You won't use the bulbs at all.
Okay. So if my bulb is burnt out, should I try and get a replacement, or should I just explain that it's broken and like for the current measurement, all I need is 1 bulb anyways, right?
But did you already filmed it?
Well, no. For
the multimeter quiz.
yes and no, but
I mean,
I'm
if
not completely finished with it, so I do still need the bulb technically, but
yeah, just email Tyler and then he can make arrangements with you to get you a new one.
well, should I get it or because I mean I have to. Sierra's like 45 minutes away from me,
Oh,
so should I go over and get it or should I just?
oh, if you don't want to drive down, then I would just go get one, if you don't mind, because they're not expensive.
So you do want me to have one though?
Well, just for as long as you can do the multimeter quiz. If you're done with the multimeter quiz, then you don't need one.
Well, I'm saying yeah for the multimeter quiz. Like, do you want us to have both of them to prove that it works?
Yes.
Or can we explain? Okay.
Because otherwise, you're not going to be able to hook them up in series. Because
Yeah. Okay. That
because
makes sense, yeah.
in step 3, you're going to have the 2 light bulbs in series, and you got to measure the voltage across one of the bulbs. And if one of the bulbs is burned, you're going to get 0. All right, because if one of the bulbs in series dies, then you get nothing. Does that make sense?
Yeah.
Okay.
Oh, and actually, my second question is, yeah, when is you said Lab 2 got moved to like what did you say Friday?
The Saturday.
Saturday,
I put it October 3rd.
All right.
Any other questions? My guess is you'll have more questions on this next week. I need to talk more about this next week. I need to talk more about the diode next week. Okay? 'Cause I ran out of time. Normally I can go through this lab quickly, but because we're online, it takes a long time to go through it. I was going to show you a demo. If you guys... I'm still here. The internet connection's bad, I guess. Can you still hear me? The video's frozen. Okay, I was going to do a demo. Okay, maybe I can try to do a real quick demo. If you guys don't mind. More for fun, I guess. Okay, give me a second here. All right, so I have a Wim Hurst generator. So I have a device called a Wim Hurst generator. And I got this to work on Friday, so I'm going to try it, hopefully get this to work today, as long as this works. That's not good. Hold on a second. Okay, so I have this plate with conductors in them, and the conductors, there's a gap in between the conductors. So I'm going to turn the lights off a little bit. Let's see if I can get, let me know if you can see. I'm going to charge the Wim Hurst generator, and I'm going to put a big voltage across this board. I think I just killed my screen. You guys see that? You guys see the flash? Okay, I'm going to stop because one of my computer screens is not happy. Okay, so basically what I've done is I put a large voltage across I put a large voltage across this thing, and every time once the charge built up, it would arc across the conductors. Okay, all right. So I won't do the other one. I'm kind of concerned because one of my screens was not happy with me doing that. Every time it arced, my screen turned off. So I will stop here, and I'll see you guys on Friday. Okay.